Alright, welcome back to another video. In the last video we learned how to manually intervene in the CSPF calculations based on bandwidth of a link. If we had a 1 gig link, we learned how we can make it so that no more than a particular percentage of the link is used. And we also learned how we can have traffic over an LSP and MPLS affect each link utilization as that traffic increases. It can either stack onto the most heavily used link until it's out of bandwidth and then stack on other ones. It can stack onto the least used links to spread the traffic all over, or it can just randomly choose which links to use. But yeah, so we finished that completely. So now we're going to be moving on to traffic engineering, as it's the traffic engineering database. So I was able to find some resources to look at in the last video. I had some extra time. So let's dive right into that. Okay, so the first two resources will just be for the regular method using help apropos, and I did that at the end of the last video, so I won't need to do that again. I'll just read aloud the resources that I found at the end of last video. So the first one is going to be help topic MPLS TED accuracy. Okay, and let's see if there's any hidden options. Sometimes there are hidden options to where help apropos can't give you the whole story, but that's not the case here, and hopefully that's pretty rare. I've really only seen that once so far. Alright, so this is improving traffic engineering database accuracy with Rsvp path error messages. An essential element of Rsvp-based traffic engineering is the traffic engineering database. The traffic engineering database contains a complete list of all network nodes and links participating in traffic engineering, and a set of attributes each of those links can hold. For more information about the traffic engineering database, see constrained path LSP computation. One of the most important link attributes is bandwidth. Bandwidth availability on links changes quickly. Before I move on, I'm gonna... Oh, this isn't even plugged in anymore. Yeah, I was just using the kitchen. The kitchen is literally across the wall, so it's a little bit... There's some like strong smells in here. Bandwidth availability on links changes quickly as and the other thing is I put my audio up a bit higher because I was doing a late night video where I couldn't speak as loud, so I'm gonna move that down. So my loudest loud is just at the top of the green and not into the yellow. Okay, so this looks a lot better, so let's continue. Bandwidth availability on links changes quickly as Rsvp LSPs are established and terminated. It is likely that the traffic engineering database will develop inconsistencies relative to the real network. These inconsistencies cannot be fixed by increasing the rate of IGP updates. Link availability can share the same inconsistency problem. A link that becomes unavailable can break all existing Rsvp LSPs. However, its unavailability might not readily be known by the network. When you configure the Rsvp error hold time statement, a source node, ingress of an Rsvp LSP, learns from the failures of its LSP by monitoring path error messages transmitted from downstream nodes. Information from the path error messages is incorporated into subsequent LSP computations, which can improve the accuracy and speed of LSP setup. Some path error messages are also used to update traffic engineering database bandwidth information, reducing inconsistencies between the traffic engineering database and the network. You can control the frequency of IGP updates by using the update threshold statement. See configuring the Rsvp update threshold on an interface. This section discusses the following topics: path error messages, identifying the problem link, configuring the router to improve traffic engineering database accuracy. So this is where my helper script comes in handy, because I can look in that. And let's just take a quick look. Nope. So I don't have it set up on these. So this is where it could come in handy though, because I could search through all of the documentation for this extra stuff. But of course, as we saw in the video where I did that, I forget what it was, many videos ago, I would need to sit and wait for 10 to 15 minutes for it to complete, which, even though it's a 6-hour exam, that's just too much time. And not only that, I need to memorize the script and type it out. So, alright, but let's cross this off. I read the whole thing. I can't really say that I understood it, but hopefully it becomes more clear as we move on. So the next part is going to be help topic MPLS traffic engineering. Okay, so this is configuring traffic engineering for LSPs. When you configure an LSP, a host route, a 32-bit mask, is installed in the ingress router toward the egress router. The address of the host route is the destination address of the LSP. Typically, you configure the BGP option, traffic engineering BGP, allowing only BGP to use LSPs in its route calculations. The other traffic engineering statement options allow you to alter this behavior in the master instance. This functionality is not available for specific routing instances. Also, you can enable only one of the traffic engineering statement options: BGP, BGP-IGP, BGP-IGP-both-RI ribs, or MPLS-forwarding at a time. Note: enabling or disabling any of the traffic engineering statement options causes all the MPLS routes to be removed and then reinserted into the routing tables. You can configure OSPF and traffic engineering to advertise the LSP metric in summary link state advertisements, LSAs, as described in the section advertising the LSP metric in summary LSAs. The following sections describe how to configure traffic engineering for LSPs. Okay, I don't see anything here specific to the traffic engineering database, TED, so I think I'm gonna call this one good and then move on to the next resource. Okay, so this is MPLS traffic engineering configuration. MPLS and traffic engineering. Traffic engineering allows you to control the path that data packets follow, bypassing the standard routing model, which uses routing tables. Traffic engineering moves flows from congested links to alternate links that would not be selected by the automatically computed destination-based shortest path. With traffic engineering, you can make more efficient use of expensive long-haul fibers, control how traffic is rerouted in the face of single or multiple failures, classify critical and regular traffic on a per path basis. And I don't see it listed anywhere, but okay. Because I want to say right now that in order to do any of this traffic engineering, you need Rsvp, but oh yeah, okay. So yep, you can see as we read forward, we're going to see what components are required to set up traffic engineering. So let's continue on. This looks like a great document to read. The core of the traffic engineering design is based on building label switched paths, LSPs, among routers. An LSP is connection oriented, like a virtual circuit in frame relay or ATM. LSPs are not reliable. Packets entering an LSP do not have delivery guarantees, although preferential treatment is possible. LSPs also are similar to unidirectional tunnels in that packets, and we got the leaf blowers going, so I will put on a pair of these. Okay, so oops, I got them on. They're kind of molded to my ears. Okay, yeah, that's much more comfortable. An LSP is connection oriented. So packets entering an LSP do not have delivery guarantees, although preferential treatment is possible. LSPs also are similar to unidirectional tunnels in that packets entering a path are encapsulated in an envelope and switched across the entire path without being touched by intermediate nodes. LSPs provide fine-grained control over how packets are forwarded in a network. To provide reliability, an LSP can use a set of primary and secondary paths. LSPs can be configured for BGP traffic only, traffic whose destination is outside of an autonomous system, AS. In this case, traffic within the AS is not affected by the presence of LSPs. LSPs can also be configured for both BGP and Interior Gateway Protocol (IGP) traffic. Therefore, both intra-AS and inter-AS traffic is affected by LSPs. Now, one thing though that it didn't mention though is I don't think you can use CSPF if it's inter-AS traffic, because you're going to have different SPF calculations. So you can't, I wish you would say that explicitly somewhere, but that's my understanding of when you need to disable CSPF is if you have a inter-AS traffic. MPLS traffic engineering and signaling protocols overview. Traffic engineering facilitates efficient and reliable network operations while simultaneously optimizing network resources and traffic performance. Traffic engineering provides the ability to move traffic flow away from the shortest path selected by the Interior Gateway Protocol (IGP) to a potentially less congested physical path across a network. To support traffic engineering, besides source routing, the network must do the following: compute a path at the source by taking into account all the constraints, such as bandwidth and administrative requirements. Distribute the information about network topology and link attributes throughout the network once the path is computed, reserve network resources, and modify link attributes. When transit traffic is routed through an IP network, MPLS is often used to engineer its passage. Although the exact path through the transit network is of little importance to either the sender or the receiver of the traffic, network administrators often want to route traffic more efficiently between certain source and destination address pairs. By adding a short label with specific routing instructions to each packet, MPLS switches packets from router to router through the network rather than forwarding packets based on next hop lookups. The resulting routes are called label switch paths, LSPs. Label switch paths, or LSPs, control the passage of traffic through the network and speed traffic forwarding. So you can create LSPs manually or through the use of signaling protocols. Signaling protocols are used within an MPLS environment to establish LSPs for traffic across the transit network. Junos OS supports two signaling protocols, LDP and Resource Reservation Protocol, Rsvp. Okay, that's interesting because I thought it wasn't that you could create LSPs manually or you could create them through the use of signaling protocols. I thought it was you can create an LSP manually if you are using Rsvp, but if you use LDP, the LSP is created automatically, and there's no way to create an LSP without using some kind of signaling protocol. Because what it's saying here is that if you neither use LDP nor Rsvp, you can still create a manual LSP. And that is different than how I thought it. So I'm going to write down what I thought versus what the doc says. And as we go forward, we might hopefully get the true answer. So I really have a solid understanding of where I was wrong. And of course, if it turns out that I'm right, we can always hit that thumbs down, and hopefully Juniper will update the doc. And I think that's always a good thing to do. The last video might have been a video before that, but we actually read that the Juniper documentation, widespread throughout all of Juniper, actually listed a mathematical equation for bandwidth with the comparison operator flipped. So I think it was saying it was less than when it needed to be greater than. So it definitely is important to report any issues because things definitely do slip through the cracks. Okay, so let's say doc says, and then it's going to be this. Oops. Where is this? Oh, down here. So this is what the doc says. You can create, and let's not use Notepad, let's use WordPad because we do want some formatting. Okay, so here's WordPad. So the doc says you can create LSPs manually or through the use of signaling protocols. And now let's say I thought you can create LSPs manually if you are using the signaling protocol Rsvp. So I thought, so this is what the doc says, and this is what I thought. You can create LSPs manually if you're using the signaling protocol Rsvp. If you are instead using LDP, the LSPs are created automatically. There is no way to create an LSP if neither Rsvp nor LDP are used. So the doc says you can create LSPs manually or through the use of signaling protocols. I thought that you can create LSPs manually if you are using the signaling protocol Rsvp. If you are using LDP instead, the LSPs are created automatically. But there is no way to create an LSP if neither Rsvp nor LDP are used. This is what I thought, and I think I'm wrong on this, but I just want to capture this thought to really kind of understand where my thinking broke down, and hopefully fix that. So yeah, so let me read this again. You can create LSPs manually if you are using the signaling protocol Rsvp. If you are using LDP instead, the LSPs are created automatically. But there is no way to create an LSP if neither Rsvp nor LDP are used. Perfect. And another thing you can do is you can have, so it's not that you can only use one or the other, but you can use both LDP and Rsvp, but you're essentially not using them together. You're just creating a Rsvp LSP, and then you're tunneling LDP over it. So it's not like you're using them in tandem for some shared goal. It's that you're building a bridge, and then you're laying the asphalt over the bridge. Like, they're not. They basically are, in some sense, an either-or type thing. Oops, that's interesting. I was about to say my toes are like pretty itchy, and now I look at my toes and they're like all like swollen, and I mean, I'm in Texas, so I bet you I got like an ant in my sock or something that like stung me a few times. Oof, but I was not expecting that. I wonder if I can. No, I don't see it. But yeah, it was like, because I'm wearing special socks, and I'm using a special powder too, because I've had athlete's foot for a while, and like this I'm surprised this powder is no longer working, because it was really effective. And, oh, it's just literally, wow. Okay, wow, that. Okay, wow. Okay, well, I'm just going to continue. My foot is very red right now, with 2 huge bite marks on it. So, yeah, well, okay. But, I mean, it just itches a little, but let's try to stay focused, because this test is going to be really important. So let's try to just, I think I'm going to pause the video right now. Maybe I have some sort of like salve or something I can put on it. So I am going to pause the video, maybe get like some ice or a salve, and then I'll be right back. Alright, so I am back. I've got I do have some cell. I have Neospore. I'm kind of tempted to actually show it on camera, but as I've said many times, this channel is what this channel is about. So, oh man, that feels a lot better. Okay, so I try to keep on topic as best I can. It's in case you couldn't tell, it's often difficult at times. But yeah, this cell is definitely taking the pain and itching away. And I hadn't planned to do any intensive walking or anything until much later in the day, so hopefully it starts to get better. I've got my ice maker on as well, so I'll be icing it up because my foot is in pretty dire conditions right now. I'm not sure what I got stung by, but I mean, it was probably an ant. I'm guessing. I don't see any ants, and I didn't see anything in my sock, but I definitely did get stung by something pretty badly just now. Okay, but in any case, let's continue on with studying for this. Hopefully I don't get stung again by something, especially since that thing is probably still here somewhere. It's probably a spider or an ant. But yeah, let's perhaps not worry about the severe itching in my foot right now. It's not searing pain, it's just itching, so it's really not that bad. So I'm going to put these back on, and I'm going to just continue the reading. We've got what the documentation says here. We've got what I thought, which is likely wrong, so let's continue reading, and hopefully we can get the true answer. Signaling protocols are used within an MPLS environment to establish LSPs for traffic across a transit network. Junos OS supports two signaling protocols, LDP and Resource Reservation Protocol, RSVP. MPLS traffic engineering uses the following components: MPLS LSPs for traffic forwarding, IGP extensions for distributing information about the network topology and attributes, constrained shortest path first, CSPF, for path computation and path selection, RSVP extensions to establish the forwarding state along the path and reserve resources along the path. Junos OS also supports traffic engineering across different OSPF regions, but in that case I believe you've got to disable CSPF if I'm correct. Traffic engineering capabilities: the task of mapping traffic flows onto an existing physical topology is called traffic engineering. Traffic engineering provides the ability to move traffic flow away from the shortest path selected by the Interior Gateway Protocol, IGP, onto a potentially less congested physical path across a network. Traffic engineering provides the capabilities to do the following: route primary paths around known bottlenecks or points of congestion in the network, provide precise control over how traffic is rerouted when the primary path is faced with single or multiple failures, provide more efficient use of available aggregate bandwidth and long-haul fiber by ensuring that subsets of the network do not become overutilized while other subsets of the network along potential alternate paths are underutilized. Maximize operational efficiency, enhance the traffic-oriented performance characteristics of the network by minimizing packet loss, minimizing prolonged periods of congestion, and maximizing throughput. enhance statistically bound performance characteristics of the network, such as loss ratio, delay variation, and transfer delay, required to support a multi-services internet. Components of traffic engineering in the Junos operating system OS. Traffic engineering is implemented with MPLS and Rsvp. Traffic engineering is composed of 4 functional components: packet forwarding component, information distribution component, path selection component, signaling component. So this is actually perhaps a bit much. I don't know if I want to do 1,000 videos on this. It's already 34. So I'm going to try to limit this down just to information about the actual database. It looks like whenever I click the find button here, oh, okay. That looks a lot better. For a while it was actually moving the dialog box. Okay, so the first use of the word traffic engineering database in this document begins here. So let's begin reading with configuring passive TE mode here. And then we'll just kind of spot read anytime the traffic engineering database keyword shows up. So the first time will be here, so let's spot read this paragraph here. To flood this link address information with the AS and make it available for traffic engineering calculations, you must configure OSPF passive mode for traffic engineering on each inter-AS interface. You must also supply the remote address for OSPF to distribute and include in the traffic engineering database. Okay, so this looks pretty good here. So this is the information distribution component. Traffic engineering requires detailed information about the network topology as well as dynamic information about network loading. To implement the information distribution component, simple extensions to the IGPs are defined. Link attributes are included as part of each router's link state advertisement. ISIS extensions include the definition of new type length values, TLVs, whereas OSPF extensions are implemented with opaque link state advertisements, LSAs. The standard flooding algorithm used by the link state IGPs ensures that link state attributes are distributed to all routers in the routing domain. Some of the traffic engineering extensions to be added to the IGP link state advertisement include maximum link bandwidth, maximum reserved link bandwidth, current bandwidth reservation, and link coloring. Each router maintains network link attributes and topology information in a specialized traffic engineering database. The traffic engineering database is used exclusively for calculating explicit paths for the placement of LSPs across the physical topology. A separate database is maintained so that the subsequent traffic engineering computation is independent of the IGP and the IGP's link state database. Meanwhile, the IGP continues its operation without modification, performing the traditional shortest path calculation based on information contained in the router's link state database. Okay, so we got plenty. Now here's the 4 things it called out before. It looks like only for 2 of them do we have mention of traffic engineering database. So this one we'll just read here, and then we'll skip those other 2 components because we just want to learn about the traffic engineering database for now. Path selection component. After network link attributes and topology information are flooded by the IGP and placed in the traffic engineering database. And excuse me for a minute, I need some more Neosporin here. Alright. Okay. After network link attributes and topology information are flooded by the IGP and placed in the traffic engineering database, each ingress router uses the traffic engineering database to calculate the paths for its own set of LSPs across the routing domain. The path for each LSP can be represented by either a strict or loose explicit object. An explicit route is a pre-configured sequence of routers that should be part of the physical path of the LSP. If the ingress router specifies all the routers in the LSP is said to be identified by a strict explicit route. If the ingress router specifies only some of the routers in the LSP is specified as a loose explicit route. Support for strict and loose explicit routes allows the path selection process to be given broad latitude whenever possible, but to be constrained when necessary. The ingress router determines the physical path for each LSP by applying a constrained shortest path first CSPF algorithm to the information in the traffic engineering database. CSPF is a shortest path first algorithm that has been modified to take into account specific restrictions when the shortest path across the network is calculated. Input into the CSPF algorithm includes topology link state information learned from the IGP and maintained in the traffic engineering database, attributes associated with the state of network resources such as total link bandwidth, reserved link bandwidth, available link bandwidth, and link color that are carried by IGP extensions and stored in the traffic engineering database. Administrative attributes required to support traffic traversing the proposed LSP, such as bandwidth requirements, maximum hop count, and administrative policy requirements that are obtained from user configuration. As CSPF considers each candidate route and link for a new LSP, it either accepts or rejects a specific path component based on resource availability or whether selecting the component violates user policy constraints. The output of the CSPF calculation is an explicit route consisting of a sequence of router addresses that provides the shortest path through the network that meets the constraints. This explicit route is then passed to the signaling component, which establishes the forwarding state in the routers along the LSP. Okay, so I'm going to skip this part because there's no mention of the traffic engineering database. So I'll just come down here, and this is limitations of an interior gateway protocol. While each individual IGP has its own advantages and limitations, the biggest limitations of IGP in general are performance and scalability. IGPs are designed to handle the task of acquiring and distributing network topology information for traffic engineering purposes. While this model has served well, IGPs have inherent scaling limitations when it comes to distributing large databases. IGPs can auto-detect neighbors with which they acquire intra-area network topology information. However, the link state database or a traffic engineering database has the scope of a single area or AS, thereby limiting applications such as end-to-end traffic engineering, the benefit of having external visibility to make better decisions. For label switch networks such as MPLS and generalized MPLS, GMPLS, most existing traffic engineering solutions work in a single routing domain. These solutions do not work when a route from the ingress node to the egress node leaves the routing area or AS of the ingress node. In such cases, the path computation problem becomes complicated because of the unavailability of the complete routing information throughout the network. This is because service providers usually choose not to leak routing information beyond the routing area or AS for scalability constraints and confidentiality concerns. So right there, this I believe is kind of speaking towards a scenario where CSPF has got to be disabled. And it kind of, I think, aligns with what I was saying before. Okay, so this is implementation. In Junos OS, the IGPs install topology information into a database called the Traffic Engineering Database. The Traffic Engineering Database contains the aggregated topology information. To install IGP topology information into Traffic Engineering Database, use the set IGP topology configuration statement at the edit protocols ISIS traffic engineering and edit protocols OSPF traffic engineering hierarchy levels. The mechanism to distribute link state information using BGP includes the process of advertising the traffic engineering database into BGP-TE import and installing entries from BGP-TE into traffic engineering database export. Okay, so here's the main section. Yeah, I'm glad I highlighted that, otherwise I might have not gotten to this until 100 videos later. Okay, so this is the traffic engineering database import. To advertise the traffic engineering database into BGP-TE, if you'll excuse me for a minute, I'm gonna see if I've got any ice, and I'm gonna ice this up as I'm reading. I'll be right back. Alright, and I'm back with some really good news. My ice maker was able to make 1 cube in this time, but I think that's all I'm gonna need. Okay, so to advertise the traffic engineering database into BGP-TE, the link and node entries in the traffic engineering database are converted into the form of routes. These converted routes are then installed by the traffic engineering database on behalf of the corresponding IGP into a user visible routing table called LSDIST.0 on conditions subject to route policies. The procedure of leaking entries from the traffic engineering database into LSDIST.0 is called traffic engineering database import, as illustrated in figure 1. Okay, here's figure 1. So here's that process. Okay. There are policies to govern the traffic engineering database import process. By default, no entries are leaked from the traffic engineering database into the LSDIST.0 table. Starting in Junos release 17.4.R1, the traffic engineering database installs Interior Gateway Protocol IGP topology information in addition to Rsvp TE topology information in the LSDIST.0 routing table as illustrated in figure 1. Prior to Junos OS release 17.4R1. Okay, and this is starting to get a lot better now. The swelling is still bright red, but I no longer got 2 raised bumps with a sting mark in the middle of them. Okay, so let's continue on. So starting in Junos OS release 17.4R1, the traffic engineering database installs interior gateway protocol IGP topology information in addition to Rsvp TE topology information in the LSDIST.0 routing table as illustrated in Figure 1. Prior to Junos OS release 17.4R1, the traffic engineering database only exported Rsvp TE topology information. Now you can monitor both IGP and traffic engineering topology information. The BGP-LS, I'm not sure what that means, reads IGP entries from LSDIST.0 and advertises these entries into the BGP peers. To import IGP topology information into BGP-LS from LSDIST.0, use the set BGP-LS configuration statement at the edit protocols MPLS traffic engineering database import IGP topology hierarchy level. I really hope I don't need to know any of this because it's just a lot, but I have a feeling I have to know all of it. Okay, so this is the next section here that I would need to read. I'm kind of tempted to just stop it here for a bit. My foot is still kind of messed up. But I think I'm definitely going to, at the very least, just bookmark where I left off. It looks like I did have another resource, so I think I'm going to look into that a little bit closer. Okay, and this will be for video 2. Okay, but let's see what that other resource is, and with any luck I'll be able to just delete it because it won't be relevant. So it looks like it's the same. Yeah, it's the same resource. It's just a different section of it. So, yep, it's not going to be important. Okay. Yeah, so let's see if we can get through the export section. I think maybe, yeah, just down to this cross-compatibility, we can skip that because it doesn't have any mention of the traffic engineering database. So I've got about 8 minutes, more like 7, so let's move on this. Traffic engineering database exports. BGP can be configured to export or advertise routes from the LSDIST.0 table, subject to policy. This is common for any kind of route origination in BGP. In order to advertise BGP-TE into the traffic engineering database, BGP needs to be configured with the BGP-TE address family and an export policy that selects routes for redistribution into BGP. BGP then propagates these routes like any other NRLI. BGP peers that have the BGP-TE family configured and negotiated receive BGP-TE NLRIs. BGP stores the received BGP-TE NLRIs in the form of routes in the LSDIST.0 table, which is the same table that stores logically originated BGP-TE routes. The BGP-installed routes in LSDIST.0 are then distributed to other peers like any other routes. Thus, the standard route selection procedure applies to BGP-TE NLRIs received from multiple speakers. To achieve interdomain TE, traffic engineering, the routes in LSDIST.0 are leaked into the traffic engineering database through a policy. This process is called traffic engineering database export, as illustrated in Figure 1. There are policies to govern the traffic engineering database export process. By default, no entries are leaked from the LSDIST.0 table into the traffic engineering database. Note, for SDN applications such as PCE and ALTO, the BGP-TE advertised information cannot leak into the traffic engineering database of a router. In such cases, an external server that peers with the routers using BGP-TE is used to move topology information up into the SCI/orchestration system that spans the network. These external servers can be deemed as BGP-TE consumers, where they receive BGP-TE routes but do not advertise them. Okay, so I think I'm going to stop it there. Next, we're going to be reading about assigning credibility values, and then after that we've just got a few more sections where the traffic engineering database is mentioned. So it looks like we do have an exercise we can go through as well to get a better understanding. Yep, so we're going to be verifying the traffic engineering database entries. Perfect. So yep, this is I think like most of my videos, not just a one video topic. So let's make a note of where to pick up in the next video. And for now, this is going to be it for video 1. So thanks for watching, and see you in the next one.